자, 이제 이 다음 강연을 또 청해 들어볼 텐데요. 우리가 우리의 미래를 가장 빨리 그래도 볼 수 있는 것이 영화 속이죠. 우리가 몇 년 전에 봤었던 영화 속의 정말 첨단 기술들이 불가능해 보였는데 하나둘씩 우리 곁에 다가오고 있습니다. 저도 몇 년 전만 해도 뭐 터미네이터도 그렇지만 마이너리티 리포트에서 톰 크루즈가 이렇게 장갑 같은 것만 끼고 키보드를 움직였을 때 정말 신기하다고 생각을 했는데 그것이 생각보다 몇 년 전에 벌써 이미 다 개발이 돼서 실용화가 되고 있었죠. 자, 이번에는 아마 영화 얘기를 조금 해주지 않으실까 싶은 분을 모시겠습니다. 스타워즈 에피소드 7의 가상현실을 구현한 ILM의 연구 리더이자 현재 University of Southern California의 교수로 재직 중인 하오 리 씨의 강연입니다. 이번의 제목은요, Democratizing Human Capture: How Depth Sensing Technology Will Change Us. Depth Sensing, Depth, 깊이를 느끼게 하는 그런 센서에 관련된 이야기일 것 같습니다. 여러분 큰 박수로 환영해 주시기 바랍니다.
Thank you so much for having me here. It's a great pleasure to give a talk at Tech Plus. My name is Hao Li. I'm an assistant professor at the University of Southern California. And prior to that, actually I just started 3 months ago, and prior to that I was at a company called Industrial Light and Magic, which is responsible for Star Wars movies and Jurassic Park and a lot of other movies. So my research is in the domain of computer graphics, bordering computer vision. And as you've seen before, we have a lot of talks today about fabrication, 3D printing. And more specifically, I'm looking at the other side of it. The other side is about how do you capture things from the physical world and bring it to the digital world. So it's all about 3D scanning, right? It's the other view of it. So I'm going to give you a little overview of, just showcase you several highlights of my past research and also how it will impact consumer-level technologies of the future, bringing basically technologies that you see in visual effects into everyone's pocket. All right, so let's get started. Traditionally, people use, acquisition systems to build models and also to capture performances. So I'm very interested in recreating, bringing characters to life. So here's an example from Avatar where people recreated, measured human performance by just looking at where motion capture balls are actually moving in space. So you can see that people have to wear these really uncomfortable suits in order to bring these characters to life. And they do exactly the same thing on the head, right? They're basically placing a camera there and measuring facial performances. And through this approach, what you can get is you can basically track what the actor is actually doing. And this is not very comfortable. So in an ideal world, what if we can do this, right? Capturing someone just by looking at a camera video, and you can have basically a digital character moving exactly in the way that the actor would be performing. Unfortunately, that's actually a very, very difficult problem, actually known in computer vision, that it's just almost impossible to automatically analyze what the video is actually doing of this person, tracking all the information and bring this into the digital character. So in this pipeline, what's actually happening is that someone is performing, you're capturing the performance, and next of it, you have a human brain, an artist, who's interpreting this information and using his imagination to bring it to life. Now the question is, what are we going to do with this imagination? How can we automate this process? So since the beginning of my PhD, I've been looking at different sensing technologies and trying to think of what would be the type of capturing system that can actually allow you to do this. So one area that has been very promising is the area of 3D scanning, where you can actually automate the process of measuring what's happening in the physical world. So here's a demonstration of basically a very established technology where you can just place an array of cameras and directly measure the physical world through an algorithm called multi-view stereo. It's static. So what can we do with it? So the idea here is that we also want to capture motion at extremely high resolution. So the thing that we did is we basically look at different technologies that have been developed like 10 years ago. And one of the very promising ones was in depth sensing. So the idea is real-time 3D acquisition way before you even had technologies like Connect. So in this case, you can see this is a demonstration of a structural light system that we developed at ETH Zurich. Basically, it's a video projector that projects a specific pattern onto the actor. That was me a long time ago. And you can actually see machine vision cameras that solve for triangulation in real time, and you can actually measure a three-dimensional representation of space. What does that mean? What it means is that you can actually look into the output of it, which is just a point cloud, and you can deduce what the emotions of the person is actually doing. It means that you can capture reality at very high resolution, things that you couldn't be able to do if you're applying markers on it. So the question is, these systems, the problem is that these systems only capture a very small volume. So what if you wanted to capture an entire human body? So fortunately, my colleague at the University of Southern California at the Institute for Creative Technologies have built this gigantic dome. It's basically a light stage 6, and the idea is that it projects it illuminates the scene, the performance of the person with different illuminations, and based on the shading on the surface, you can actually deduce the three-dimensional point cloud out of it, right? So you can actually capture, measure human performances, wearing clothes, really complex geometries happening, and you get these like high-resolution 3D point clouds. My research is about trying to make sense out of these point clouds. There are two problems in these point clouds. First of all, you can see there are obviously some holes in it. The scanner is not going to reach in occluded regions. And the second problem is the machine doesn't understand this information. This information is simply just like a huge bunch of point clouds that are being measured. So we want to be able to analyze this information. And the key answer for that is an approach called dynamic shape reconstruction in order to find correspondences in the data. So here's a simple example. So if you see on the left, this is an input seen from a single 3D camera. And what you see on the right, this is what you could, in theory, get if you put one single model and you can actually capture the full performance of it. Actually, this is a very non-trivial problem because what it involves is the ability to tell the machine to find correspondences over time. So you basically here have like a sequence of hands that are captured at different instances in time. And let's have a look at how we solve this problem in the case of a pair of scans. So what you want to do is, I mean, for a human, it's very easy to tell, right? You can see that the tip of the finger is matching to the tip of the finger at the other instance, but how can you tell the machine this? In order to tell this to the machine, you need an optimization framework. And fortunately, because we're not in a space of analyzing images, we're really having three-dimensional point clouds. And if we have three-dimensional point clouds, we can do numerical optimization at a geometric level. So here's how it works. So we came up with a solution of having this non-rigid registration algorithm, which does the following. So you have a source and you have a target scan, and what it does is it automatically warps the source onto the target without requiring a person to manually label what is going where. So this thing is completely automatic. So you can see the process. It's actually warping one scan onto another. And what you get out of it is the following. First of all, the two scans have been captured at two different instances at a time, and you can't know, the computer wouldn't know where correspondences actually exist. So you can first identify overlapping regions, and the second thing what you get, which is the most important one, you get full point-to-point correspondences. Well, you can do this on scans. You can actually just follow the stream of points that are actually going through these scans, and you can do markerless tracking by doing so. But more interestingly, what you can do is the following. Instead of having just scans, you can replace one scan with a model, with a devised model that has been created by someone, and you can do data fitting, right? It's what everyone does in statistics and machine learning. You're trying to have a model and fit this model onto specific data. So the gray one is the data, the blue one is the model, and here's just a demonstration how robust this actually system is. And it basically is just based on a convergence, right? It's a little bit like gradient descent, if you know that. And it basically warps this model, a different person, a different pose, onto the data that you're scanning. Why would you want to do this? Well, if all the information is in the model, you're basically transferring real-world measurements into a knowledge, right? And you can basically immediately let the computer understand what kind of shape you're measuring. You can do body shape statistics. You can directly animate the person. You can basically measure body mass index or all sorts of statistics. And in the space of computer animation, you can have a rigged model automatically, and something that typically would require an artist to do. So you can do these things computationally. Here's other examples that you can do in the space of in entertainment and visual effects. Traditionally, if you wanted to create something that is physically real, very complex, what you need to do is you need to have an artist model a specific creature, or in this case, a puppet, and you would have to apply physical simulations on top of it. It's very computationally expensive. It's very difficult to even tweak the parameters. That's why visual effects companies spend millions of dollars just to produce very specific shots. What you can do with measurement technology is that you can immediately measure what is actually happening in reality. But the problem, it's not that easy. It's not like you just measure and everything just works. The problem here is that you have these occluded regions and you have a correspondence problem in order to do post-editing. And you're just shifting the problem into something different. Here's another example, and that is very cool because what you can instantly do is markerless facial performance capture, simply by using a structural light system. And even more, you can even create details, you can transfer details that you see in the future and in the past and warp them into specific frames in order to get more details, super resolution, things that you couldn't do by just applying motion capture dots. Here's another example of what you can do by warping future and past information to current frames. You can actually fill in holes. The input is what you see on the left, output is what you see on the right, and you can basically see how you can actually fill in holes just by using this correspondence warping, right? And you can do exactly the same for the texture. So these are great examples. You're always using some form of templates, but they're not only specifically designed for humans. It can be applied for anything. It can be used for fluids, for example. So here's a neat demonstration of topology changing phenomenons that we can also do tracking on it. You can do it for maybe fluid mechanics, or you can simply, for animation, you can have higher detailed fluid simulations. So this is nice. All the examples I've been showing you before were all in the realms, in the space of entertainment, gaming, films. But these technologies are not limited to it. They seamlessly carry over to other sciences, for example, in biology. So here's an example of a work by the University of Geneva, where evolutionary biologists have actually applied this technique in order to discover the scaling effects, the scale of crocodile skins. They actually happen through physical cracking and not through an evolutionary process. Here's another example, collaboration with the Washington University. What we've been trying to do here is trying to establish a direct link between cardiac surface mechanics and electrophysiology, which is basically how electricity changes on the surface of the heart. And the purpose here is really to find the connection between these two models in order to have a better understanding on how the heart works, why we have cardiac diseases, and also how to fabricate better drugs. So it's sort of like a quantification method, and it's completely markerless. It captures at 666 hertz. So we have an extremely high fidelity measurement on what is actually going on. This next project is a very cool one too. You can basically use graphics that are developed for Hollywood and use them to treat cancer, right? So this is a technology that is used, that I've done in collaboration with a company called C-Rad Electa. And the idea here is that we are able to track a tumor inside the body of a cancer patient in real time just by measuring how the surface is actually deforming. So we're basically applying non-rigid registration algorithms in order to find correspondences that happen through time and do a real-time physical simulation underneath the body in order to measure where the tumor is. Now the next step is that all these examples that you have seen have been, in research lab, in visual effects studios, but the real big impact is that these things are no longer part of these industries, but is also going to have a big future for everyone. So there's a huge massification, democratization of these technologies, and Microsoft did the first step by launching the Microsoft Kinect, which is basically a depth sensor for less than $100, actually $100. So what they did in the first place was they actually started this future vision concepts. It's basically a video that Microsoft produced, and at that time, a lot of these things seemed really like prototype, right? A little bit like science fiction, but I have to say that a lot of these applications are in development. So there are a lot of startups that have actually made these things possible, and these kind of sensors will have a very impactful future. So I'd like to show you a live demonstration right now on how this is happening actually also in the space of facial animation, in the space of entertainment. Can we actually, sorry, my system crashed, so I have to restart, unfortunately. Sorry about that. I think we're good on time. All right. I can actually show this afterwards while it's actually rebooting. So let me just continue the talk. So, so basically the system I'm going to show you right now, hold on a second, is an effort that we have been pushing at Industrial Light and Magic, which is we were trying to investigate on the possibility to improve virtual production, to make it real-time using extremely high-quality, high-fidelity renderings. And the purpose there was to see if there's anything we could do with faces. Because if you're producing high production value movie, faces are really important. They actually have all the expressions of the actor. And I'm sorry, it's doing some updates right now. Maybe I'm having problems with the internet connection. Oh, that might take a while. All right, let me just go on first, and I'll show this probably later. All right, so just imagine you'll see a real-time demo of a facial animation. And so what we are going to do next is the following, is that the demo that I was about to show you was actually animating creatures, right? Non-human faces. And if you want to create realistic human faces, you want to do head replacement, then the challenge is twofold. One is the rendering, and this has been more or less solved actually as a collaboration between USC ICT and Activision. You basically can have a really high fidelity facial performance in real time using a playback. But in order to capture the performance directly, that still requires a lot of work. And the second thing that's very difficult is you have to have the capability to deal with robustness issues, especially when you're doing all these kind of processing in the wild. All right. So, we've seen a lot of bold heads. And one other challenging problem in the field of computer graphics is hair, right? How can you do facial animation without having realistic hair? So in collaboration with Princeton University, we've developed a system that takes an array of camera, large array of cameras, and just by taking a single picture, you can generate hair fully automatically. So here's an example. So on the left, you can see this is the input image of one of these cameras, and the algorithm automatically generates strands of hair. Oh, it booted. Let me just start. Let's hope it works now. It does. All right. Let me first see. Okay, there you go. Can we switch to the other laptop? Thank you. Can you guys see? Huh? Okay, so this is basically the input. This is what this Kinect sensor is actually seeing. It's actually from PrimeSense. So it's a three-dimensional depth sensor. The red dots are features that are tracked on my eyebrows, my eyes, and my lips. And what I'm going to do now is I'm going to do facial animation. So it has to load some data of some characters in the background. So it'll take a few seconds. Yes. There you go. Huh? So on the left, the input. In the middle, my tracked face. So it's doing what my face is actually doing. And you have this angry baby that's like just being animated. And I can also be a little monkey. All right, that was a little demo I wanted to show you. If anyone is interested, we can talk about that later. Let's switch back to the other slides. Looks a little bit shaky when I'm not there. All right, so these kind of technologies, you can use it for a lot of things, right? For computer animation, the big impact is that you have basically a system that understands what your facial animation is actually doing at the moment, right? It's instantaneous. It doesn't require you to sit in a controlled environment to do physical measurements or training the system, having an artist in between tweak things. It just works. So here's another project, something that I'll be presenting next week at SIGGRAPH Asia. The idea is to have the ability to digitize your entire body simply from your home, right, in your living room. So what we did here is we just have a Kinect. This is a collaboration with Artec. We have a Kinect on a tripod, and you're just like doing a certain pose, turn around, and what it does, it's basically collecting tons of different point clouds of your body from different sides, and just by pressing one single button, you can recover the shape of your body. So the difficulty here is I'm not using a turntable. I'm not using specific illuminations. It basically is smart enough to actually warp everything together and to recover a seamless three-dimensional object. So this is going to be a free software that you can actually download. It's called Shapeify Me. And obviously, the first thing you can do, you can just do 3D printing. So you can have like a three-dimensional photograph of yourself and have fun with it. The second thing that you can do with it, so here are a few other examples. You can do more complicated things using props, using a chair, having thick clothing. So it's not making any assumptions about a human body. It can be anything. So the other thing is it can also revolutionize the way we do personalized gaming. Yeah? We can create virtual avatars of yourself inside the game. This is actually a digital body of myself that I just captured in my living room. And together with a software called Smart Bodies from USC ICT, we could actually just drag and drop this three-dimensional scan of yourself into the software, and it rigs your body. So you can automatically generate animation. These are movements I've never done. So you can do other things. If you have body measurements at home, just think of the virtual clothing industry, right? If you can have a way to have customized tailoring, this will basically change the way we'll do online shopping. Right right now you'll still prefer to go to a shop, but if someday you have the way to actually have an accurate measurement of your body, even without taking off your clothing, that would actually change the world. So here are just a few more examples on why I believe that depth sensing technologies are going to be, they're an emerging technology, but they're going to have a huge impact in the future, because these things are not just toys, right? So a lot of camera companies are actually looking into building these kind of sensors. Obviously, Microsoft is leading the trend right now with this Xbox. It's going to be in the living rooms. People are investigating the use of depth sensors with tablet devices, right? You can actually have, by just locating where your tablet is, you basically can enrich reality with interesting digital content. You know, just think of augmented reality. And the other thing is you're going to have depth sensors in laptops. Just think of a way of interacting with three-dimensional digital content, of doing real-time hand tracking. So this is a demonstration from a company called 3 Gears. It really works. You basically just put a Kinect on top of your laptop, and you can measure very precise hand measurements beyond of other technologies. And finally, here's just an example of a company called Pelican Imaging that is exploring the use of having depth measurements in your cell phone. So just think of like some future applications where you can actually change the way we would think about like producing three-dimensional photographs and ways of storing and sharing our memories. All right, so I'd like to conclude my talk. Thank you so much for listening. My name is Holly from USC. Thank you very much.